This is an hourglass. It measures the passage of time by dropping a constant flow rate of sand. But here's the question, does the weight of an hourglass change when the sand is flowing versus when the sand is stopped? This simple question has confused physicists for decades. In fact, if you look through different physics books, you'll find completely different answers. Some say it gets lighter, some say it gets heavier, and others say it stays exactly the same. Well, I have a sensitive scale here that can give me weight updates every 1 millisecond. So let's test this and actually see what happens. So first, why would we think the weight could decrease? Well, let's look back at an earlier video I did where I took a completely closed container with a weight attached to the top. When that weight was released, the reading on the scale decreased by the weight of the object because it's now in free fall. So if the hourglass constantly has some sand in free fall, then it seems obvious that the reading on the scale should decrease by the weight of the sand that's currently in free fall. So this is option 1. But the astute scientist will say, yeah, but wait a minute. Yes, there's some sand in free fall, but there's also sand hitting the bottom. That impact will exactly counteract the missing weight of the sand in free fall. So the net force change is exactly 0, meaning there's no change in weight. So this is option 2. But wait, says the even more astute scientist, if you look at the sand at the top of the hourglass, those grains are moving downward with some velocity. It is slow, but they're actually moving. Then compare that same sand once it's reached the bottom, it now has 0 velocity. So if you look at the net result, you had some sand that was moving and then it suddenly came to rest. So there should be a force equal to the mass flow rate times the velocity of the sand at the very top of the hourglass there. So the weight will increase by that amount. So this means the hourglass should weigh more when the sand is flowing versus when it's not flowing. So we literally have 3 good arguments about what should happen. But which one actually happens? Well, let's check. But before we continue, I want to thank the sponsor for this video, Dreame. This is the Dreame X60 Max Ultra Complete. Now, the thing that surprised me most is just how thin this robot is. The robot vacuum is only 7.95 centimeters tall, which makes it one of the thinnest robot vacuums out there. What's cool is that the top sensor actually automatically lifts when it's in open space and retracts when it goes under furniture, so it can clean places that most robot vacuums just can't reach. Another thing that's really interesting is that it can actually detect dirt in real time. The front camera uses a light-assisted system to identify things like dust, hair, and even lighter colored stains. When it detects something, a blue light turns on and it automatically adjusts how it cleans, switching between sweeping and mopping depending on the mess. And it's powerful too. The X60 Max Ultra Complete has up to 35,000 pascals of suction, plus a detangling duo brush system designed to pick up hair and debris from both carpets and hard floors without getting tangled. Another feature I thought was really clever is that it can actually climb obstacles up to 8.8 centimeters tall. So things like rug edges, door tracks, or small transitions between rooms aren't even a problem. And navigation is pretty impressive. It uses an AI-enhanced OmniSight system with dual cameras, which helps it recognize and avoid things like cables, toys, or other objects on the floor, while mapping out the most efficient cleaning path. But probably the most convenient part is the all-in-one power dock. When the robot finishes cleaning, it goes back to the dock where it can automatically empty the dustbin, and it refills its water tank and cleans and dries the mop pads with hot air, and basically gets itself ready for the next cleaning cycle. So if you want to check out the Dreame X60 Max Ultra Complete and see all the details, you can check the link in the description below. And thanks to Dreame for sponsoring this video. Now let's get back to our video. Okay, now let's test this out. I'm going to be using a 1-minute sand timer so we have a higher flow rate and we don't have to wait as long. I'll set it on the scale here, and we're going to look at it when it's flowing and then see if it changes when it runs out. Okay, it does not look like any change happened here. Just have a flat line. But let's look at the raw data and take the average before and after just to be sure. So there's no statistical difference between the before and after here. So it looks like there was no change. So after this, I can see that the logic of option 1 is flawed because it ignores the sand hitting the bottom. And the logic of option 2 seems pretty solid, and it looks like this might be the right answer. But there's still a problem here. In order for the force from the striking sand to completely cancel the missing weight of the falling sand, we had to assume one thing, that the sand starts its free fall with zero velocity. But you can tell this isn't the case. Look at the sand flowing into the neck. It already has velocity before it starts free falling, so the starting velocity isn't zero. This means that over a given amount of time, the sand is hitting the bottom with slightly more force than we assumed. So the true equation isn't just force equals the mass in free fall times the gravity. There's an extra term that comes from the change in momentum due to that initial velocity. So the true force should be different by the mass flow rate times this small velocity. But it turns out that this force is very tiny. Even for this 1 minute sand timer, it was so minuscule that I couldn't detect it on my sensitive scale here. So if we're going to see this effect, we need to make a weird hourglass. One where the sand at the top is moving faster than in this 1 minute timer. To do this, I can make the cross-sectional area much smaller near the top, essentially turning the top into a long, narrow neck. But the difference in the velocity of the sand at the top is much higher because the area is smaller than before. So the bottom of the glass is hanging in the air here. The neck comes up. It's attached to the scale here. It's a really long neck. Okay, I'm going to pull off the bottom here. Okay, that's the blip where I pulled off the tab. So let's look at the raw data and see what this looks like. Already I can see that before and after it stopped, there is a difference. It weighs about 0.25 grams more, about 250 milligrams when the sand is flowing compared to when it's not flowing. So option 3 really is the right answer. This is so counterintuitive, to think that the hourglass weighs more when the sand is flowing in a closed system than when it isn't. But for any realistic hourglass, the velocity of the sand at the top is so slow that there's no measurable change in force. For a real hourglass like this one here, the change in force would be extremely small, somewhere in the microgram to nanogram range. I like this demonstration because it's a good example of an old engineering saying that goes like this: there's what's true and there's what matters. In this case, option 3, the hourglass weighs more when the sand is flowing. This is the correct answer. But when the effect is about 1 part in hundreds of millions, it doesn't really matter. So I'll leave it up to you to decide what answer you would give somebody. Maybe this is a good question to place bets on. Whatever the person says, you can give an alternate answer. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you haven't subscribed to my channel yet, remember to hit that subscribe button, and we'll see you next time.